good afternoon to everybody, yeah, and welcome to this lecture number 9. And you probably remember that last time, yeah, we established that the surface brightness of an extended object, yeah, in the focal plane of an interferometer, yeah, is just a convolution product, yeah, of the intrinsic source intensity brightness distribution, which is, well, I would just make use, yeah, of this, yeah. So this is a intrinsic surface brightness distribution of the object, yeah, convolved with the response function, yeah, of the interferometer. Now, where the quantity, so this is the response function, yeah. Now, the first quantity, so this one, yeah, represents in fact, yeah, the response function, so the point spread function of one of the two apertures, yeah, composing the interferometer. And now when you combine the two apertures, yeah, well, you have to add, yeah, this cos squared term, yeah, where D is a baseline between the two apertures. Now, well, I just remind you, yeah, that for the case, I just remind you that the response function, yeah, of a single aperture for the case of a square aperture, yeah, has the following shape, yeah. So this is the distribution you see here in the pupil plane. So the complex distribution of the amplitude, which is constant, and when you perform, yeah, a Fourier transform and take the square of the modulus of this Fourier transform, you get the response function, yeah. And we see here that there is something looking a little bit, yeah, like the airy disk, but it's not an airy disk, yeah. There is more square features, and the angular resolution, and the angular resolution, yeah, of this aperture, yeah, is in fact the distance between the two minima on both sides of the emission peak. And so it is 2 lambda over A, where lambda is a wavelength, yeah, or of the pseudo monochromatic light, yeah, and A, the side of the square. Now, for the case of a circular aperture, where we've seen that, well, it's not anymore, yeah, the square of a single function, but it's the square, yeah, of a first order Bessel function. And so this is aperture, which is circular. And now the distance between the two first minima, so here is the first minimum, here is the second minimum, is in this case 2.44 lambda over D, where D is the diameter, yeah, of the aperture. Well, of course, when you use your interferometer with these two apertures, yeah, you presuppose that none of the single aperture is capable of resolving the source, yeah, and therefore you use an interferometer, of course. Now I go to the next page here, and what you see here is just for the case when the two apertures are square. What is the response function, yeah, of the interferometer? And here we see the signature of the cos square function, yeah. So we see that, well, there are intermediate minima. Now the continuous line that you see here, yeah, is the response function of a single aperture, but the presence of the two apertures, yeah, leads to the cos square terms, yeah, giving rise, yeah, to, well, minima which are much nearer to each other. Now here, the distance, angular distance between the two minima, in this case, yeah, is lambda over D, where D is the baseline, yeah, between the two single apertures. Okay. Now, let's see how the previous convolution, yeah, gets simplified, yeah. I told you that, yeah, well, O of PQ, which is intrinsic, yeah, surface brightness distribution of the extended source, yeah, looks more like a delta function, a Dirac function, yeah, with respect to the response function of the single aperture. And this is the reason why you may take this term, yeah, this factor, out of the convolution product. Yeah? So this time, this factor, yeah, is simply multiplied by the convolution product of the intrinsic source distribution by the cos-square term. Yeah? Yeah, so now, well, in the lecture notes and in the video, yeah, that you had to look for this lecture, you could see that we treated a very similar case, but assuming that the source shows some symmetry. And here, what I'm just presenting to you is a case when we know nothing about the structure of the source, so it can be asymmetric. Yeah. So now, what we do, we make use of the trigonometric relation, according to which the cosine of 2 times x is equal twice the cos square of x minus 1. Yeah? So we will replace in this relation this cos square. I try to underline it. Yeah? So this term, yeah, by means of this relation. Yeah? So you see appearing here a cosine, yeah, of 2 pi pd, yeah, which is this quantity, if you want. And then the 1, yeah, just appear in this form, yeah? And then we divide by 2, yeah, which is the factor 2 that you see here. So divided by 2. Now I will just move a little bit my slide up. Yeah. Now what we do, yeah, we take this term and put it in front of this bracket. Yeah. So we have this first factor multiplied by this second one. Now you see here there is a 1 appearing. And now this convolution product, yeah, must be divided by this integral. Yeah, it's what you see here. Yeah. Okay, now we redefine, yeah, the normalized intensity distribution of the source, yeah, by the following quantity. So O prime of PQ is equal to O PQ divided by the integration, yeah, of OPQ as a function of dP. Now, this factor, which I will underline, yeah, I just rename it as being the quantity A, so it's more simple. And so that we may rewrite, yeah, this expression in the following form: the surface brightness distribution of the source in the focal plane is equal to the constant A multiplied by 1 plus the convolution product, yeah, of the normalized intensity distribution of the source, yeah, by the cosine term that you see here. And now, well, in the next slide, what we will do, yeah, we shall detail this convolution product, yeah. So we will represent it, yeah, as a double integration on some of the variables. Yeah. So we go now, we jump to the page 3, and you see here, well, this is the convolution product that you have seen before, which has been detailed. Yeah, so it's a double integration of the normalized surface intensity multiplied by this cosine term. Yeah, and we integrate here in the variable r and s. Now, we still simplify this form. Yeah? You know that a cosine, yeah, can be represented as a real part, yeah, of a complex exponential function. Yeah? And it's what we do here. We replace, yeah, this cosine by the real part, you see here, yeah, of the complex exponential function, which consists of 2 terms. Yeah? You have first the 2 pi pd that you see here with a minus sign, 2 pi rd minus 2 pi rd, and then the other one, 2 pi pd, appears here. Yeah? And this second factor, yeah, may run away from the integral because it doesn't depend on the variable r. Yeah? Now we define a new quantity, which is in fact, yeah, the normalized slice intensity of the source. Yeah. So you see that indeed we have integrated the previous one. Yeah. With respect to the variable s. Yeah. Because if you look here in this double integration, we see that the s variable doesn't appear in the cosine. Yeah. So we may perform directly the integration on the s variable. Yeah. So by defining this new normalized quantity, and by defining what you see here, the integration of O tilde time this complex exponential function dr, well, is nothing else than a Fourier transform of the normalized intensity of the slice of the source. Yeah? So you see this one appears here. And well, I've named it gamma. Why gamma? It's because we have already seen in some of the previous lectures that this is the complex degree of mutual coherence of the source. Yeah? This is the definition. Yeah? Now, since it is a complex quantity, you may represent it as a product of its module by the complex exponential function where you introduce well, just a phase shift beta. So this is a normal way to represent a complex quantity. And we may then rewrite the previous expression, so the surface brightness distribution in the focal plane of the interferometer as a multiplicative constant A by 1 plus. Now, if we take the real part of all these, while substituting these two quantities, we see that, well, there is a module of gamma, which appears here. And now after, you must take the cosine of this one, of this quantity here, but plus the beta. And therefore you see here appearing beta, which is a phase shift of the fringes, in fact, in the focal plane of the interferometer. So I just put it a little bit above, And well, we already derived such a relation for the case of a two-point-like apertures in the past. But now we are dealing with the finite-size apertures. And you see, well, that we obtain exactly the same relation. So, well, we redemonstrate, in fact, the Zernike-Van Sittert theorem. Now, if you would like to know what the visibility of the fringes becomes, what we do, we say, okay, the visibility is the maximum of this function minus the minimum of that function divided by the summation of the two. Now, how do you get the maximum? Just by setting here the cosine equal to 1, plus 1. How do you get the minimum? By, well, assigning a value of minus 1 to the cosine. And when you make those replacements in this definition of the visibility, what you obtain is that just the visibility is equal to the module of the quantity gamma, which is the complex degree of mutual coherence of the source. So it is in fact the module of the Fourier transform of the normalized intensity of the slice of the source for each angular value well, across it. So we have now recovered the important result, the Zernike-Van Sittert theorem, which first has been established for the case of two-point-like apertures. And according to it, the visibility of the fringes is the Fourier transform, well, is a modulus of the Fourier transform of the normalized intensity distribution of the source. Now, previously, we have applied that relation by assuming that beta is equal to 0. And this is typically the case when your source shows some symmetry. But when the source has a known shape, well, the complex degree of mutual coherence can be a complex quantity. And well, this will result just in a translation of the fringes in the focal plane. And during well, the last lecture next week, I'll show you with GeoGebra what happens when we observe a symmetric source and an asymmetric source. And you will understand how it's possible to measure this value of the phase shift. But I don't go through that demonstration now. So I will just delay it here for next time. Now, what comes next? So, next now is about the Wiener-Khinchin theorem. Yeah. So this was part also of the lecture and of the video that you probably have visualized. Yeah. And well, the demonstration is of course in the lecture notes and on the videos. I'm not going to repeat it here. But what is very nice is that when you make the Fourier transform, yeah, of the response function of an instrument, well, in our case, yeah, it's an interferometer composed of two apertures separated by a baseline D. You demonstrate that the Fourier transform, yeah, of the response function, yeah, so of the intensity of point-like stars that you observe at the focal plane of the interferometer is just an autocorrelation function, yeah, of the distribution of the complex amplitude, yeah, in the pupil plane. So now to visualize this, yeah, we have represented here on the upper left side, yeah, the distribution of the complex amplitude, yeah, in the apertures, yeah, of an interferometer consisting of two, yeah, circular apertures, yeah, two cylindric mirrors with a diameter A. And when you just make an autocorrelation, yeah, of these two, so you just shift, yeah, the two well along the y direction. And of course, when this one, yeah, will come on top of the other one, yeah, you will get, yeah, this central peak. When this one will go on top of the left one, yeah, on each side, yeah, of half the baseline, yeah, you'll get, yeah, this well, half height cones, yeah, and this gives you a good idea, you know, of how well you cover the UV space, yeah. So here we see that for the case of single aperture, yeah, where we cover very low spatial frequencies, and thanks to the interferometer, we may get access, yeah, to higher spatial frequencies, yeah. So you see that maximum here in the center, and well, less sensitivity, yeah, for those spatial frequencies, yeah, located here at the edges, yeah. So this gives you a good idea when you will be observing, yeah, an extended object, yeah, which spatial frequencies, yeah, you will be able to reach and to use. Now, well, what comes next, yeah, is just something to think about, yeah. We have demonstrated, yeah, that for the case of a circular aperture, yeah, the angular resolution, yeah, is lambda over d divided by 2.44, yeah. Well, I could have written it as a 2.44 lambda over d, where d is the diameter of the circular aperture, but I prefer to write it in this way. Now, for the case of a square aperture, which side, yeah, is A, well, we have seen that the angular resolution is lambda over A divided by 2, yeah? And now for the case of an interferometer, the spectral resolution is lambda over B divided by 1, because it's lambda over B. And what you see here is that, well, here we have a factor 2.44, here is factor 2, and here a factor 1, yeah? Yeah, which means the following, that if you would use, yeah, a circular aperture, cover it, yeah, with cardboard, and just put, well, at the edge of this circular aperture, two little holes, yeah, separated by a distance d, yeah, this would give you an angular resolution equal to lambda over d, yeah, where d is the diameter of the mirror, yeah. So you see that even with a circular mirror, you could increase its angular resolution by just covering it, you know, and just piercing two small holes, yeah, well, with the longest baseline, yeah. So this is very interesting. And this is a technique that has been used by many astronomers from a single aperture mirror, circular ones. So they just put a cover and made use of just the light coming from two holes located at the edge of the mirror. And then you increase the angular resolution from 2.44 lambda over d to lambda over d. So you see there is a gain. So this is quite interesting. So this is a summary of the content of lecture number 9 that probably you have been visualizing, or maybe you have been reading the lecture notes. And before to continue to something else, I would like to give the floor to the participants for eventual questions.
Okay, thanks, Jean.
So this lecture,
have any question?
It was quite a lot of theory, but now, will become time, to make it in practice, But it's not difficult, But one has to really concentrate, trying to understand very well the different concepts, But everything has been demonstrated in the lecture notes, and also in the video, So, the questions now.
You guys can unmute and ask any questions you have.
So, but if there are no questions, I may continue, and go.
Can I
please.
make a comment, John?
Please, Dash.
Okay. I just want to clarify on one of the issues which can confuse the listeners. Is the word resolution is really ability to resolve. Should not be confused with lobe separations and the apparent ability to distinguish cases which are, where the sources are nearby and so on and so forth. So in principle, the ability to resolve does not improve as dramatically as it might appear from the equation of lambda by b by using two holes at the ends of the big mirror. The ambiguity of which lobe it is in, the source, will continue to exist. So in principle, whenever you have a single aperture and you make two such apertures and separate them by a certain distance, you will find the ability to resolve or ability to pinpoint the direction has improved only by a factor of 2, strictly. The lobe spacing is now reduced, and so you can see sensitivity of small movements, noticeable because of the lobe separation. So I just wanted to make this distinction, because whenever I used to, in my early days, used to call it an improvement in resolution, I was always stopped and reminded of this fact, that actual resolution and the fringe spacing should not be confused.
Sure. So I was really referring to the fringe spacing. I absolutely agree with you. It's very important. But just to make sure that the distance between the two minima, so which is the fringe spacing, will decrease in the way I've just shown. But this is not absolutely. It's along one direction. Because of course when you use a circular aperture, immediately you get improvement in angular resolution along all the directions, rather than with an interferometer, you only get one direction, And as I said, what you obtain is just some information, on the normalized intensity of the slides of the source being perpendicular to the baseline,
No, the point is, John, that if you move, for example, if you wanted to pinpoint the direction of the other source could be in any location separated by integral multiples of the fringe spacing, and one would not know. And so that's the point I'm trying to make, that the ability to resolve is there, better than single aperture, has improved it by a factor of 2, but you now have the ambiguity of which lobe it is in.
Sure,
you
I
can
agree.
now differentiate between ups and downs of the fringe, which are much closer. And so it might give one an impression of an apparent dramatic increase in the resolution, but it's only a factor of 2. It is the lack of further increase is folded in the inability to distinguish between which lobe of the fringe the sources are, because they are indistinguishable.
Yeah, I agree. And then, well, therefore, it's very good, to change the length of the baseline, right?
Right, right.
There's a question in the chat window, a related question, which says, what is the criteria to say two sources are resolved?
Yeah. Well, Rayleigh gave a definition. Well, just assuming that the two sources are equally bright, you could say, well, it's just a matter of well, there is no single definition of when two sources are resolved. But if you take two equally bright sources, you just say, well, they will be resolved whenever the angular separation is, for instance, will have the separation between two dark fringes. Okay, but you could, it's just a matter of well, adopting a definition, which is quite arbitrary. Now, if the two sources are unequally bright, when are you certain that you resolve them? Also, this will depend on the signal to noise that you have in the data, etc., etc. So, well, I would recommend that you just look in Wikipedia, the Rayleigh definition of when two sources are resolved. And well, what is being stated is that, well, if they're equally bright, they will be resolved whenever the angular separation is half the distance between two minima. So maybe, Desh, do you see another way of answering, replying to this question?
So just to be clear, the definition changes for different cases? That's a follow-up.
Yeah, I think it's really ability to unambiguously, distinguish between two sources. It's more qualitative, and as John rightly said, it's also a function of signal to noise ratio. For example, even if they were very close and you could distinguish with very high signal to noise ratio that it differed from a single source model, then you can, after all, you can also look at it as a simple modeling exercise, that your source distribution is a model, let's say, and you're trying to fit that with, after convolving it with the response function, with what is observed. Now, how well you can distinguish a single source model from the depends on what the signal to noise ratio allows you to see the sensitivity. And so it's finally boils down to this. Imagine the least square fit of model source distribution with the response function of your instrument, be it interferometer or be it single aperture. And then you're trying to see which one fits better. And so that, as you will see, depends almost entirely after the nominal resolution has been specified for the instrument, entirely on the signal to noise ratio.
Yeah.
And this is what was shown by Peter Scheuer in the context of lunar occultation, the diffraction patterns, you get of the edge diffraction. You can actually, with improvement in signal to noise ratio, you can get higher and higher resolution. So to the first order, you will find that the resolution is really given by 1 upon the signal to noise ratio and some measure of sharpness of the response, which can be characterized by square of the first derivative of the function integrated over the span, over the coordinate. So there is in the context of pulsar timing and so on, these things are very nicely discussed. I can send you a reference, and that will give you an ability to distinguish or measure the location, like in astrometry, how accurately you can pinpoint the direction. That will depend on the sharpness of the response function and signal to noise ratio.
Yeah. Now, just to add something, well, more specific, maybe to the question raised by the participant, is that it depends on the signal to noise ratio, but it depends also on the flux ratio between the 2 point-like sources that you're looking at. Yeah? And as Professor Desch mentioned, the best you can do in that case is just to make simulations. Yeah, just make simulations for different flux ratio, for different signal to noise ratio, and different angular separations. Then, well, you get a quite good understanding about what you're doing. Yeah, so don't take for granted, that, well, angular resolution, is just one definition. Yeah, one should look, with very careful, look at very carefully and with great caution. Yeah. Yeah. Now, well, I just seen in the chat that someone said, well, but since the atmosphere is changing with time, so how do we do? Well, the best to use adaptive optics. Yeah. And for interferometry, well, it's really a must. Yeah. So above each single aperture, people are using adaptive optics. Yeah. But then what you don't know is what is the piston. Yeah. It means the difference in the height of the atmosphere above one aperture with respect to the other. Yeah. And well, this piston effect will just have for effect, to shift, the fringes, as a function of time, with a very high frequency, where sometimes the period of those variations can be a few milliseconds, and for that you would like to integrate those fringes. So what you need to do is to make use of a fringe tracker, So in the optical plane, of the interferometer, there is a mechanism which allows you to follow these very rapid shifts of the fringes and to integrate. So better is the atmosphere above the interferometer, where longer can be the integration times, and fainter, deeper can be your observations. So this is a part of the answer to the questions that has been raised about the changing atmosphere. One thing I wanted to show you now is about the UV coverage coming from the rotation of the Earth, so that it will be more intuitive for some of you. And to do that, I would like to share my screen. So well, I prepared a video, but I'm scared about showing the video because you remember last time, the computer got blocked. But what I will do instead, is just showing you a globe, representing the Earth, seen from a distant star, So, well, here's a star looking at the Earth, and well, on the Earth, you see that there is an interferometer, a bit looking like the VLA, but there are only, I think, 10 antenna. And well, as the Earth rotates, you see that the projection of the baselines change well, in size and in orientation. Yeah? So we'll just move on. So the Earth is just rotating around the south-north axis. Yeah. Yeah, and this is what the star sees, yeah, from your interferometer. Now, what I represented, yeah, on this slide, yeah, is our three baselines: one in yellow color, one in red, and one in blue. Now, at another time, almost when yeah, the star see at best, yeah, the interferometer. So you see the three baseline, yellow, red, and blue, and still at another time. Now, what is shown on the next view graph, yeah, on the next slide, yeah, are these three projected baselines seen at three different times by the star, yeah. So this was at the beginning. So I will show you. I come back here. So you see, I'm just representing this one, yeah. So it's here, coming here, and coming back. Now this is the other one, and what is very well seen here, yeah. So I just drew. I mean, the projection of those baselines is that, well, you see the red baselines here is shorter, much shorter than here, and definitely its orientation, yeah, change as a function of time. Yeah? So it's the same, yeah, for the blue and yellow baselines, yeah. And well, during the next lecture, yeah, I'll give you some hint how to calculate, yeah, for a given latitude, a given declination of a star, and a given hour angle, the projection of the baselines, yeah, of an interferometer located on the ground, yeah. So it's something very easy to do, and well, I propose to do that during the next lecture. Now, the last thing I wanted to show you, yeah, is a video. What it should illustrate, yeah, is just the path of the shadow of a street lamp projected on the ground in the parking of my observatory in Liège, Belgium, yeah, on the 22nd of September in 2019, yeah. So in 2 more days, yeah, you should be able to see something similar. It's okay. You see here is a projection, yeah, of the shadow of the street lamp, which is here. So it's time lapse, yeah, that was done, yeah, during about 6 hours of time. And of course, now you see those images, yeah, being projected with some acceleration. And well, I just mentioned the problem last time, yeah. What should be the trajectory, yeah, of the solar disk projected on the ground, or of a shadow, yeah, projected on the ground, yeah, at the different times of the year, yeah. And what is very funny, and is that on the 22nd of September, well, the equinox, yeah, the trajectory, yeah, followed by the shadow should be a straight line, yeah. And this is true, yeah, wherever you are located on the Earth, yeah, at the pole, North Pole, yeah, or at the equator, or in India, yeah, or anywhere else, yeah. And well, the reason, yeah, is simply that on the equinox day, the sun is in equatorial plane, yeah, which is perpendicular to the north-south axis, yeah. And of course, I mean, this equatorial plane, yeah, in principle pass through the center of the Earth, yeah, but we are not far from the equator, yeah, with respect to the distance to the sun, yeah. So it is just as if the equatorial plane, yeah, was passing, yeah, through your eye, and so the sun, while rotating around this north-south axis, yeah, is in a plane. So the shadows, yeah, are projected from a plane onto a plane, and the intersection of two planes, yeah, is a straight line, yeah, and it's what you, in principle, yeah, could see in that video. And well, if you do the same experiment, yeah, during well, the solstices, yeah, winter or summer solstice or winter solstice, yeah, what you would see most of the time is that the trajectory is no longer, of course, a straight line, yeah, that it is a branch of an hyperbola. But sometimes, depending on where you're located, yeah, it could be a circle, it could be an ellipse, it could be a parabola, yeah. And this is a very nice illustration, yeah, of the existence of conic curves, yeah, in nature. Yeah? So nature has invented everything for us. Yeah? Okay, so I will stop here, and I'm ready, yeah, to answer questions which could be related, yeah, to with the previous topics or to anything, you know, in being part of interferometry.
So thanks, Jean, for very, very instructive and clarifying simulations and these last two demonstrations.
With pleasure. Yeah, we just love with my wife, yeah, to take many time lapse, and we have many others, and yeah, it's really very nice, you know.
Yeah, it's beautifully illustrating the actual thing at hand, you know, of how the baseline orientation and length changes.
Yeah.
Thanks, Sean. There was a question earlier about physical significance of autocorrelation.
About what?
The physical significance of autocorrelation. I think they want an intuitive understanding.
Yeah, I think for me, you know, it's very intuitive. Yeah, when you make the Fourier transform, yeah, of the response function of an instrument, yeah, well, you get the Fourier components, yeah, which are accessible, yeah, at well, some available frequencies, yeah, space frequencies, yeah, and so, of course, when you make this autocorrelation, you get it straight away. Yeah, you see that you remember there were three cones for the case of an interferometer. Well, the central cones is, of course, the autocorrelation, yeah, of one aperture with itself, yeah. And so if you take, yeah, two circular aperture, make the autocorrelation function, of course, you get that cones. And, well, it corresponds absolutely, yeah, to the space frequencies, yeah, which you may access, and then there is a cutoff. You know that you cannot get higher frequencies than something like d over 2.44 lambda, yeah. And when you make the same autocorrelation, yeah, of the two apertures, yeah, well, you know, you just translate, yeah, these two, and you see which higher frequencies, yeah, you may get access to, yeah. So for me, it's of course it's not obvious. I mean, I don't think anyone, yeah, could have predicted, yeah, that it was such a simple relation, but it's really very lovely. And if you go through the demonstration, it's very simple, yeah, and straightforward. If you make use, yeah, of all the relations, yeah, pertaining, yeah, to Fourier transforms that have been described, yeah, by Professor Desch, yeah, and by myself also, yeah. But so it's very nice, yeah, that when you even try to make some deconvolution, yeah, you know that one thing you will need, yeah, is the Fourier transform of the response function of your instrument. well, namely the Fourier transform, yeah, of the image, yeah, intensity image of a point-like star, yeah. And what is very nice is that even, well, of course, if you have adaptive optics, yeah, if you cannot observe the star with your instrument, yeah, you may still derive, yeah, what it is, yeah, thanks to this autocorrelation function of the aperture, yeah, of your instrument, yeah. It's very nice, yeah. So I think, you know, you may spend some time, yeah, especially before falling asleep, yeah, to think about, yeah, well, why the two are related, yeah. And to me, it looks quite obvious that from the autocorrelation, you should get some information about the accessible space frequencies, yeah. And you know that you would get it, yeah, from the Fourier transform of your response function. Now that, well, the two are equal, yeah, this is fantastic, yeah, and very simple and very neat. Yeah, that's all I have to do to say. Maybe Professor Dash, yeah, may want to add something.
Yeah, I have just one suggestion about possible help in visualizing this. You think of the aperture at hand as made of large number of small apertures, sub-apertures. And then you will see that whenever you're squaring the output of this, you are actually having large number of interferometer spacings with the sub-apertures. And ask what spatial frequencies or baselines they are sampling with what orientation. And you will land up with this conical spread around the location that you see. So take each sub-aperture in one and each sub-aperture in the other and do all the possible combinations and count them. And that will give you the cones effectively.
Yeah, sure. Yeah, and indeed, yeah, if you take a circular mirror and just consider, you know, the holes, yeah, at the edge, yeah, well, there is only one possibility, yeah. You cannot get many such frequencies because you take the two more extreme holes, yeah. Okay, now, instead of taking a baseline of D, if you take half the baseline, yeah, so these are very near, so you know that, you know, you may just put, yeah, this pairs of holes, yeah, many more times over the aperture, so you get yeah, more answer. And well, I fully agree with you, Dash, is that it's a nice way to visualize, yeah, why it is like that, yeah. So there is a lot of redundancy, yeah, when you see the central cone, yeah, you say, wow, there is a lot of redundancies, yeah, in the space frequencies that we may get access to, yeah. And well, if we would just get, you know, no redundancy, yeah, but covering well the UV plane, this would be fantastic, yeah. And therefore, you know, with the VLA, this is one of the reasons, yeah, and I guess with GMRT as well, they didn't want to get, you know, so many redundancies, yeah, and therefore the spacing, yeah, between each interferometer along the three arms, yeah, have been well estimated, yeah, in a well, very interesting way, so that you avoid, yeah, too many redundancies, yeah. Otherwise, if they would be equally spaced, yeah, then you get much more redundancies, yeah, and well, you get this kind of conic shapes, yeah, that Professor Desch referred to. Yeah.
There's a question in the chat.
Yeah, so the UV plane image in the slides show the symmetry that comes from the transform of the real function cos square. Yeah, so, well, I mean, I'm not sure about which UV plane you refer to, yeah, but during the next lecture, well, I will, as I said, yeah, I will give, yeah, or we will establish, you know, the relations, yeah, to know how you get those space frequencies, yeah, while the Earth is rotating, yeah, how you may cover the UV space, yeah, and then, well, I think it will be a straight answer, yeah, to your question. Yeah.
May I add a brief comment? Just
Yeah, sure.
The symmetry in the UV domain is always ensured at the level of Hermitian symmetry. The amplitudes of the visibilities will be symmetric and the phase will be antisymmetric. That is guaranteed in general. Okay. And that comes from the simple fact that the brightness distribution, of which this is a Fourier transform, is real. We are looking at real quantity distributed in the plane of the sky, and that has implicit Hermitian symmetric visibility, which is a mutual coherence function, spatial mutual coherence function. That is guaranteed. And so what is shown here is the amplitude, if you like, and that will always have Hermitian symmetry. In addition, in this particular example, because one has taken the response function, which has the intrinsic symmetry and the real part that John showed, coded as a complex thing, but taking the real part of it also ensures that symmetry. So the real part has the symmetry, imaginary part has the antisymmetry, and since we are considering here only the real part of the visibility, you will find that it will be naturally symmetric. But the origin of it comes from the fact that there is a Hermitian symmetry in the visibilities, thanks to the brightness distribution being only a real function.
Yeah, during the next lecture, yeah, I'll address also the phase information, yeah, that I mentioned, because some people, yeah, could, well, some optical interferometry sometimes only make use, yeah, of the phase information, yeah, to reconstruct, yeah, well, the source images or to fit some models, yeah. While not using at all, yeah, the visibilities, yeah. Some people have done that, yeah. But well, the best is to make use of both, if possible. Yeah, some people have only made use, yeah, of visibilities, especially when you only have well, one baseline at a time. Yeah, and I'll explain during the next lecture. Yeah, how it's possible. Yeah, well, with optical interferometry, yeah, to recover some information. Yeah, from well, phase information. Yeah. Part of phase information, not totally, but well, partially, and more as you get more simultaneously observed baselines. Yeah?
I think in the chat there is, do you want me to say something about the Hermitian symmetry?
Yeah, sure.
So there is a question about the Hermitian symmetry. So Hermitian symmetry is just diametrically opposite points being complex conjugate of each other. So in the visibility domain, we do see the from the origin to be having contributions which are complex conjugate of each other. What does that mean? The real parts are same, that's symmetric, and the imaginary parts are antisymmetric. Does that answer the question, whoever asked?
I think if you refer, yeah, to the lecture notes of Professor Desch during his first lecture, yeah, well, I think that there are good examples, yeah, where all the properties, yeah, of the functions and the Fourier transform, their Fourier transform, yeah, are related to, and the Hermitian, yeah, definition is there shown, and yeah, it will be more clear if you go back to those lecture notes, I think too.
Okay. Desh, there was earlier a question about one of the questions you had suggested for the assignment, the one where there's a 2-year course and people are there are students who who take admission and they pass out in 2 years or 3 years or 4 years and so on.
Yeah, there was a query about needing some elaboration on what I mean by this cross correlate the
yes,
n out
with
and
relative
n in,
shifts,
right?
Yeah.
So if n out and n in will be functions of when you plot them, you will find a pattern which will be labeled along the x-axis with the time at which people pass out and the time at which people enter. And so those can be absolute times. And then you will find you essentially have two patterns, one corresponding to the entry number as a function of year or time, and passing out number as a function of year again or time. And my question referred to if one were to cross correlate these two patterns, would one see any similarity? And the relative shifts are basically to see, for example, since it takes 3 years to pass at the minimum, you will find even if everybody passed, 100% of the students were to pass at their first whatever minimum time of the course, you will find then that these two patterns will be identical, except they will be shifted by 3 years from each other. And so at a relative shift of 3, they will match perfectly. And here being the case of not that everybody passes after the 3 years, you will find 80% correlation will be obtained when you actually shift the thing by 3 years, because then some additional amount will be seen as a correlation corresponding to the 4-year shift when people taking 4 years will be passing out. The pattern of the entry will match in parts with the numbers that are passing out with appropriate shifts. And so that's what I meant, whether it would reveal any information about the time people take to complete the course.
No, so actually it was my question, Desh. I wanted to know, there were two things that were unclear to me. The first thing was when you ask us to plot n in, p and n out. So you
Yes.
expect us to plot. So by p you mean that I generate a column
year number.
Yeah.
The
So I
year.
generate. Okay. No, so what I was thinking was that I thought that what we were supposed to plot was that I generate a column for every p, doing 0.98, 0.2, 0.15 and 0.05, and then
Right.
plot every p individually as with respect to n in and n out.
No, they have to be superposed, and then finally, that's what the convolution will amount to.
Yeah.
Okay.
Yeah.
So the sum, and the important part, since we are on that topic, would like to underline that in the final outcome of how many people pass out in different years, you will realize that you're probing for a given time, which is the time at which people are passing out. And they will have contributions from all combinations of entry and the time they took to complete the course, such a way that the sum of the two amounts to the year of passing out. So T entry plus T stay in the course is equal to the T pass out. And this is what allows you to, when you write general probability of people passing out, you will find that it can be written as a product of the two, the number entering times the probability of passing out after a certain time. But you will find that those two times are now related, because the sum is the time at which you are probing the number. As against, in correlation, you will find the difference in time is kept constant for the probing. And all pairs which differ in their ordinate by certain separation are counted, and they contribute to the correlation. Whereas in convolution, it is the sum of the x-axis values which is conserved for a probed epoch.
Yeah. Since we are speaking about convolution, yeah, something came to my mind. Well, a friend of mine, yeah, loves to design didactical tools, yeah, on the internet, yeah. So now I'm just sharing my screen. Can you see it?
Yeah, sure, we see.
Okay, yeah. And what it shows, yeah, it's a pinhole camera, yeah, where the hole, entrance hole, yeah, is a square, yeah, and we are looking at the sun, yeah, and here you see that it's a distance of the screen, yeah, from the hole, 10 centimeter, and what you see, well, a very small, yeah, circle here represents, in fact, the size of the sun with respect to the size of the hole, and you see here, well, the yellow holes. Now you see, I'm just increasing the distance. Now I'm 1 meter 30, and we see that this is a convolution, yeah, of the square, yeah, by the sun. And well, the real image of the sun in this case would be, you know, the dotted points that you see here. Now I'm still increasing, and you see more and more, yeah, the image looks like the real image of the sun. Also, well, as you are going farther away, yeah, it's dimmer and dimmer and dimmer. But you see the edge, yeah, is not very steep, yeah, it's diffuse. It's because of the convolution, yeah. Now, well, I come back here, and you may download, yeah. So at the beginning of the PDF notes that, well, I will send to Prakash, yeah, you'll be able to find the link, yeah, to this application. Well, now I'm just, well, oh, maybe a heart, yeah, I like the hearts, yeah. So here is a hole, yeah, well, having the shape of a heart, yeah. Well, this is on a cardboard, yeah, which is white, yeah, and illuminated by the sun. And you see, if you are very near, 10 centimeter, well, you see a yellow heart. And as you go further away, yeah, this is a convolution of an heart with a solar disk, yeah. And as you go further and further away, yeah, well, it looks more and more like the real image of the sun, but still with some convolution effect, yeah, at the edge, yeah. Then, well, it is this application so that you could change the incidence angle, yeah. So if you're not perpendicular to the light rays of the sun, well, this is what you would see. Well, I just, you see, you may change the inclination and the angle, well, 50 degrees, and of course it looks like that, yeah. Now you may still download, yeah. Well, upload, yeah, another, well, mouse, yeah, or butterfly, yeah, I prefer the butterfly. So here's a butterfly, and you see, as you are very near, yeah, 10 centimeter from the screen, well, of course, it looks more or less like a butterfly, but with the incidence of 0 degree, yeah, it looks better. Now you may overlay, yeah, the grid so that you know what is the real size. Yeah? So 1 unit is 1 centimeter. So you get the relation, yeah, between the size of the image you see and the distance at which you are looking at. Yeah. So you see here I am the distance of 3.5 meter, and this is the convolution, yeah, of a butterfly hole, yeah, with a solar disk. Yeah. And as you go farther and farther away, well, you almost get, yeah, the real image of the sun. Yeah. So yeah, this is another view, yeah, of what a convolution product is. Yeah, convolving, yeah, different aperture shapes, yeah, with solar disk. Yeah. So as I said, yeah, the link, yeah, to this application, yeah, will be given right at the beginning of the PDF presentations that I'll send to Prakash.
That's very nice. Thanks, Joe.
Yeah, I know there's that you love the convolutions.
Well, they are unavoidable.
Excuse me?
I said convolutions are unavoidable.
Yeah, absolutely.
Correlations that we hold by hand, I mean, we do with hands to see the similarity. Convolutions happen naturally.
Absolutely. And it's fantastic that, you know, nature invented, yeah, a conical trajectory, yeah, of a convolved holes, yeah, or solar disk, yeah, on the ground, yeah. It's magnificent, yeah. And I think it's very good, yeah, for lecturers, yeah, to, well, introduce those notions, yeah, to the young students, yeah, by illustrating these with the natural, well, things that you may see every day, yeah. And, well, it's very nice, yeah. Yeah.
Okay, I think we covered all the questions in the chat. If I missed something, or if anyone else has any questions, they can raise now.
Yeah.
Or else we'll end for the day.
Yeah, the forum, yeah, is widely open, and yeah, we try to, you know, with Prakash and with Desh, yeah, to look at it, yeah, and to send you replies, yeah. So next time, yeah, I'll try to make to produce another GeoGebra illustration of an asymmetric source, yeah, because until now, yeah, we only looked at well, circular sources, yeah, or square, yeah. But well, it would be nice to see what is the effect, yeah, of looking at a source, which shape we don't know what it is, yeah.
All right.
Okay.
So,
So see you next week, in 1 week, for last lecture, and wish a good week to all of you, yeah. And see you soon. Bye bye to everyone.
Bye everyone.
See you all. Bye.
Bye bye.